All right, guys. So we're here. We're doing question 4 from the 2026 AP Chemistry exam that was on May 5th. Um, and so now we're getting into the shorter questions. So, right, these are only worth 4 points apiece. Questions 4, 5, 6, and 7. Let's look at the prompts. We got A, we got B, and we got C. So we got 3 prompts. That means one of them is going to be, um, one of them is going to be worth 2 points. Okay. They also, they gave us the equation. They told us what the equilibrium expression for Kp is equal to. So they were using the partial pressure notation. Remember, don't forget to square your P2 here because it had a coefficient of 2, and products over reactants. And they have a question mark here, so I'm guessing we're going to have to find Kp. So we're going to have to know this partial pressure at equilibrium. We're going to have to know this partial pressure at equilibrium. So just kind of different things, right? They bring this guy back. I forget if this was last year's exam or the year before, but kids were complaining about that. Remember last year or the year before, they gave us this structure without the lone pairs on the phosphorus. And all we had to do was finish the dot structure and add the lone pairs on the phosphorus. But anyway, we got this thing, and then we got P2, and it has a triple bond, right? So just different things. Maybe we're thinking this bond is stronger than that bond, right? This bond is shorter than that bond. Just different things you could be thinking about as you're going through the question. Okay, and they talk about the length of the bond. Okay, so we should know that, especially when it's between two of the same atoms, right? The radius of this phosphorus is the same as the radius of this phosphorus, is the same as the radius as this phosphorus, is the same as the radius of this phosphorus. So bond length, if you have bigger atoms bonded to each other, it's going to be a longer and longer bond. But remember, the other thing to remember, the more electrons that are being shared, so we're talking single bonds versus double bonds versus triple bonds, the more electrons being shared, the closer the nuclei end up getting to each other, so the shorter the bond distance. So, we already know that this is the shorter bond, and we just kind of have to explain why. And again, triple bonds are shorter than single bonds, but maybe you want to explain that a little bit more. So in covalent bonds, as long as the atoms sharing the electrons are similar in size, which is the case because they're all phosphorus atoms, the more electrons being shared, the shorter the distance between the two atoms, and so the shorter the bond length. Okay. So that's pretty quick. So here they set this up, and I think, we're trying to figure out the equilibrium partial pressures so we can plug it in to solve for the Kp. They give me the initial partial pressure of the reactant, and they give me the equilibrium partial pressure of the product. And we have to use that information to figure out the equilibrium partial pressure of P4, which is not 0.47. So we want to make sure we don't plug in 0.47 into here because that's not the equilibrium partial pressure. That's the initial partial pressure of that thing, right? So this is a great place to make a rice chart, kind of organize your work. And then once you get your equilibrium partial pressures, plugging them into the expression and solving for Kp. All right, so let's go ahead and make our rice chart. So we got our reaction, initial partial pressure, right? Before the reaction starts, we don't have any of that. So to get equilibrium, we're going to have to lose this, and we'll lose one of these. But for every one of these that we lose, we're going to gain 2 of those, right? That's our change in our rice chart. And then so at equilibrium, this will be 0.7 minus x, and at equilibrium, this would be equal to 2x. But we know what it is because they told us that in the equation that it was, or in the question was 0.363 atmospheres. So now we can solve for x. So, right, we can take this part of our rice chart and we can solve for x. So we know 0 plus 2x equals 0.3 or 0.63. So x equals 0.315. We would do our subtraction to get our partial pressure of the P4. And then remember, we're just plugging in this equilibrium partial pressure and this equilibrium partial pressure into the expression. Don't forget to square the P2 partial pressure. And we end up with 2.56 for our equilibrium constant value. Remember, we don't need units for equilibrium constants. But if we did, right, this was atmosphere squared over atmospheres. So if we did, it would just be atmospheres in this case. Yeah. All right. And then part C, the reaction is thermodynamically favored. So they're telling us right now the delta G is negative. We should understand that because the Kp was greater than 1, so we know it's thermodynamically favored. But it's only thermodynamically favored at temperatures above 1500 Kelvin. So that means sometimes it's not thermodynamically favored. So if it's below, it's not thermodynamically favored. All right. And a student claims that the reaction must be endothermic. So understand what that means, positive delta H, because it's favorable only at high temperatures. Do you agree or disagree? But you have to justify it in terms of delta S. So this is where that bridging assignment that I give you, bridging thermo, equilibrium, and electro together, and you're making all those connections, this is where that really pays off. Because we can look at the reaction and know that the delta S is positive. We're going from 1 mole of gas to 2 moles of gas. So entropy is increasing. Disorder is increasing. So delta S is positive. And if we just remember our connections, if delta S is positive and delta H is negative, the reaction is always thermodynamically favored no matter what the temperature. When you have a negative delta H and a positive delta S, the reaction is always favored. Delta G always comes out to be negative when we plug those values in to the delta G equals delta H minus T delta S equation, right? So we know that this reaction is not, we know that the delta S is positive, and we know the reaction is not always thermodynamically favored. So that means delta H can't be negative. So delta H has to be positive. That means endothermic. So the student is right. We have to agree with the student, right? So it's going to be agree because we know that delta S must be positive. Why? Because the equation shows 1 mole of gas being converted to 2 moles of gas. That's an increase in randomness. More gas particles, more random, more disorder. Okay? So if delta H were negative, the reaction would always be favored. So delta H must be positive, and that means it's endothermic. So that's why we agree with the student. Okay. All right. That's question 4. We'll go question 4 and question 5. All right. Here we go. Question 5. Here we go. We got the Lewis structure. All right. So just some things I might be thinking about, right? Tetrahedral shape. The things coming off of the carbon are not the same. So this is asymmetrical. So this molecule would be polar, right? It would have dipole-dipole interactions. It would have London dispersion forces. It wouldn't have hydrogen bonding because it doesn't have, hydrogen in it, and it doesn't have H bonded to F or H bonded to O or H bonded to N. So we know it's polar. If they ask about the hybridization of the carbon, it's sp3. If they ask us any hybridization of any atom, they all have 4 domains around them, so they're all sp3 hybridized. The bond angle would be around 109, right? The tetrahedral angle, not 90, right? It shows 90, but it's really 109. So all that good stuff. But part A is just asking which of these bonds, carbon to bromine, carbon to Cl, or carbon to fluorine, is most polar. They're all polar, all right? Well, which one's the most polar? And we should easily know that's going to be the CF because it has the bigger electronegativity difference, right? So if we go on to that question, right? CF has the bigger electronegativity difference between carbon and fluorine compared to the other one, so it's going to have be the most polar. All right, so the CF bond is the most polar, the biggest electronegativity difference. Okay. Here they talk about the bond angle. Now this is, this could be a tough question. You got to think about this, right? So a lot of times when we talk about the discrepancy in bond angle, when we talk about when something has the same number of domains, we're talking about the difference between a bonding domain and an unshared pair, and the unshared pair takes up a little bit more space than a regular bonding domain, right? So like water has 4 domains around it, and it's tetrahedral geometry, it's bent shaped, but its bond angle is around 104.5 degrees, whereas like CH4 has 4 domains, but they're all bonding domains, and it's tetrahedral, but its bonding angle is closer to 109, right? So usually we're thinking about little discrepancies in bond angles as being the difference of lone pair domains and stuff, but that's not the case, right? They're talking about this bond angle. They're talking about, it's back to this. They're saying this bond angle is shorter than that bond angle between chlorine and bromine, and right. And the reason that is because Br and Cl are bigger atoms, have bigger electron clouds than fluorine. So let me see if so again, it's going to be about the radius. And the reason why this has a bigger angle is because than this one is because the bromine and the chlorine have bigger radii. And so they can't come together to 106.8 degrees because their radiuses are too big. So they're a little bit more further apart. Okay. So here, like, right, this bond angle they were saying is around a 107, whereas this bond angle's 112. And the reason is the large size of bromine and chlorine compared to the fluorines make the bond angle a little bit wider. Okay. All right. So here we got our IMF question, the one we're always prepared for. We've been prepared since unit 1, right? They give us 2 substances, and the first thing is just list the IMFs that they all have. What we have to remember is everything has LDF, okay? And the only thing that non-polar things have are London dispersion forces. So we should recognize this as being a symmetrical molecule. So even though it has polar bonds, it's a non-polar molecule. And since this is an asymmetrical molecule, it's polar, okay? But notice the polar thing has a lower boiling point than the non-polar thing. That usually goes against what we're thinking. We're usually thinking the polar thing has dipole-dipole interactions and the non-polar thing only has LDFs. So usually the polar thing has stronger IMFs than the non-polar thing. But the boiling point is telling a different story. It's telling me the thing that's non-polar has stronger IMFs than the thing that's polar. Okay, no big deal. All right, so because the CBr4 was nonpolar, it only has London dispersion forces, okay? And because this is polar, it has London dispersion forces and dipole-dipole interactions, okay? If it was something that had a Fon bond and could have hydrogen bonding, then you would list London dispersion, dipole-dipole, and hydrogen bonding, okay? But for this one, it's London dispersion and dipole-dipole interactions, and for this one, it's London dispersion. So what must be true? Well, it must be the London dispersion forces in this between these molecules are stronger than the combined London dispersion and dipole-dipole interactions between this molecules because this had a higher boiling point, and that's what that means. Okay, so we know which one has stronger IMFs. It's this one, but its only IMF is London dispersion, so its London dispersion is stronger than the combined IMFs of this one. Okay. Now, so the London dispersion in CBr4 are stronger than the combined LDFs and dipole-dipole interactions experienced by the other molecule. This is why CBr4 has a higher boiling point. It takes more kinetic energy to break the CBr4's IMFs compared to that compound's IMFs. Now, if you want to explain why its London dispersion is so strong, it's because bromine is much bigger than chlorine and the 2 fluorines. So this has a bigger electron cloud, and it also has more total electrons because bromine's bringing a lot of electrons to the party. So more electrons, bigger cloud, greater London dispersion. And it's big enough that its London dispersion is stronger than the dipole-dipole interactions of this polar molecule. Okay. All right. So yeah. All right. So that was question 5. Next video will be 6 and 7.